What's going on, everybody? Today we're going to be going over what's called tautomerization, and that basically is the interconversion between an enol and a ketone. Remember that an enol is a vinylic alcohol, right, as shown here. But here's a ketone. We've seen ketones a million times. You learn it as one of your functional groups. And it's just the interconversion and the strong favorability for the ketone when you do produce an enol product. So let's get into the mechanism here. You're going to see this in your organic chemistry class when you talk about alkynes. Now, the reagents that are involved in a hydration of an alkyne is mercury to get the 2+ ion. You're going to do this in water under acidic conditions. All right, well, let's get right into the mechanism here. We have this alkyne here, quite simple. The first step of this mechanism is that mercury's like, what's up, dude? I'll steal those pi electrons. It's gonna form a sigma bond. Or the pi electrons are more so like, yo, dude, you're invited to the party. And we get the following compound. Let me just count my carbons. Like that, okay? And then mercury can really bind to any place here, but we'll say for the sake of this reaction that it binds right on that side. So what happens next? Well, we're gonna have a positive charge here, and that water molecule is like, I'm a brave, weak nucleophile. It's kind of like Robin and Batman. Batman's the real strong nucleophile. Robin's like the little sad guy that's kind of just there. That's kind of what water is as a nucleophile. But Robin does save the day sometimes. That water will bind to this molecule to form this intermediate. Okay. What do we know about that right there? Oxygen with a positive charge. Well, oxygen with a positive charge is a big no-no. But you probably committed that to memory. You might not know why. Why is that? Well, oxygen is very electronegative. It can't stabilize a positive charge as well as other atoms can that are a little bit farther away from the right top side of the periodic table. If you were to say that oxygen likes a positive charge, it's kind of like saying the sky is purple. The sky is not purple, the sky is blue. So let's get into what happens next with the oxygen. Well, it no like positive charge. So another Robin's clone, is gonna come and it's like, yoink, I'm stealing you. And now just dump my electrons on that positive charge. And we're gonna get the following molecule. We're gonna get an alcohol, right? Hopefully you know that. If not, it's okay. We all start somewhere. Okay. So you're looking at this molecule, you're like, ain't that an enol? Nope. You still got your mercury on there. You gotta get rid of that boy. He's no good. So how do you do this? You're gonna start by using a proton in solution from an acid, right? And what you're gonna get is the pi bond reacts with it, right? I like how I say things and I don't implicitly say them. I just assume that you people know it, but I'm just a big fat idiot sometimes. Okay. And it's gonna add to the mercury side, which is gonna cause this area to have a positive charge. Well, mercury kind of looks at that and is like, I'm so sorry, beta carbon to my left. I am so sorry. I stole your electron density. I am so sorry. So it's like, I will remove myself from this conversation. Goodbye, cruel world. And it forms the following compound. Now we have an actual alcohol. Look at that, everyone. I should probably draw this a little bigger. Hold on. I just noticed I'm drawing this very small, so it's probably hard for you guys to see. Okay, so we look at an enol and we look at a ketone. why are we going to do the next steps to make a ketone rather than an enol? Well, what does better with a double bond? Well, we know double bonds are short, okay, so we can't really compare that. Well, we can compare the atoms that have the double bond. Carbon-carbon for an enol, carbon-oxygen for a ketone. Well, we know that oxygen and carbon makes a very strong, polar, short bond. And with a double bond, that bond's gonna be even stronger and shorter. Stronger, shorter bonds means more stable. So, for that reason alone, we're gonna get the ketone. So this is quite simple how this works here. I forgot to erase an arrow from one of my last attempts. Shh, okay. I gave you a hint here. You have hydronium, which is caused by water picking up a hydrogen just naturally, spontaneously, right? So what's gonna happen is this pi bond is gonna say, what's up, hydrogen? You look like a pretty cool guy. You're invited to this party, the party of organic chemistry in my flask. And what's gonna happen is that it's gonna add away from the alcohol onto this side. So hydrogen's here, right? That side of the molecule is all happy, giddy, but that, this carbon here is just getting brutalized. Look at this, positive charge here, positive charge here, positive charge there. This damn carbon's under attack. It's getting brutalized over here, y'all. This is terrible. Well, now again, it has a positive charge. It's like for the third freaking time, man, you're doing this to me. So what's gonna happen? That oxygen's like, I'm tired of this carbon bitching in my ear. Let me elaborate the bond here so you can see the mechanism. Okay, water's like Robin in Batman. It's like, I'm coming. And it takes back a hydrogen and it dumps electrons. And then oxygen has a negative charge and that carbon has a positive charge. So oxygen's like, yo, you wanna help me out? You wanna make me more stable? I'll help you out. I'll give you electrons, homie. So it does that very thing. And you're going to get a ketone. Yippee! And that is the mechanism. Remember why we said this is favored, because the oxygen, the CO double bond, is a lot shorter and stronger than a CC double bond. That's important to know. I was gonna comment on one other thing, but I'm having a brain fart. Oh yes, this is an acid catalyzed step, this step here, because we get H3O back. So, something important to note in your lab. Let's say that you wanted to get the enol. You might think that you could do it in the freshest, cleanest flask you ever had in your little organic chemistry lab. Impossible. Even the smallest amount of acid will unfortunately catalyze this reaction, and you will get the ketone and not the enol. It's catalyzed and it happens pretty fast. Even the smallest amount over an appreciable amount of time, it will form your ketone. So when you take it into consideration, if you don't even need to draw out this whole mechanism when writing the products, you can quite literally just write the ketone instead of going through the enol and then showing the tautomerization of it. I just wanted to point that out because that's important to note, is that they'll expect you to know that tautomerization happens, not necessarily so much the mechanism, but this is very important to show you. I appreciate you guys watching this video. I hope that this was a little fun mechanism. I had a lot of fun writing this all out for you guys. I hope you guys have a wonderful day, and take care. Enjoy your organic chemistry adventures.